Okay, so I guess, yeah, it sounds like I'm attached. And get the screen back up. Takes a second. Very good. Well, I'm delighted to be here. Certainly want to express my appreciation to Laura for all the hard work she's done organizing this, and Katie Fries and Nardita for the support they've given to the whole operation. So I'm, as my title indicates, I haven't got something definite to teach you or to propose. I just have odd little bits of general relativity and gravity that intrigue me, and I will try to answer some or pose some questions, and I'm not even sure that they're not only my questions. I think the first one, someone else mentioned, can a graviton be identified? Will we ever have our hopes of actually seeing a quantum of gravity? And so I ended up doing something else that brought me close to that, so I will show you that. And then there's this question of whether the Hawking radiation, which we are concentrating our attention on for most of this meeting, the question is, will we ever have evidence that there is such a thing? I don't think there's any serious contention that it was not a soundly based theoretical prediction. It's been looked at from so many different points of view that give consistent answers. So all we know about quantum mechanics and gravity, the best we can fit them together, the Hawking radiation seems inevitable, but whether it has played a role in the development or the future of the universe remains an open question to me, at least. We're pretty, as I've heard other people mention, the black holes that we actually have on our list of almost objects in the observed sky that are almost certainly black holes, none of those would be currently losing mass due to Hawking radiation, because they're gaining mass from so many other things, including at the lowest level, the 3-degree microwave cosmic background radiation, which is much hotter than any of the black holes we know about. Now, as the universe expands, things will change. I haven't tried to follow that because eventually the universe might expand enough so that black holes can actually begin losing mass. On the other hand, who knows whether they will have gained so much in the meantime that the starting point has changed and they're even colder than we think of them now. So we don't know what's going on here. I guess I have to keep occasionally talking to this computer or it gives up. There we are. Okay. Fine. So then there's all these questions of what goes on, possibly the famous firewall just inside the horizon, and that's something I have strong doubts about because I can't, the horizon as such is normally defined in terms of the ultimate fate of light rays, and we can't look that deep into the universe to know what's going to happen to any particular light ray. The universe may change quite a bit in the future, so we're not sure what it should be. But another thing that I want to tell you about is what I call the quiet dog effects, and I'll explain that further. But that's not where you see something, but where you don't see something and can draw conclusions from that. So that's a few questions that bother me a bit. And here are a few of the things as we see. Whoop, how is this playing out on the screen? I really wanted to see the tops of these documents there. Yeah, if we can get the whole slide on one screen. There we are, much better. So these are things that I want to tell you about. Whoop, I'm going the wrong direction. There we are. So the questions, And now there's some of these things that I will try to mention. These are the pieces, just odd bits of relativity that amuse me or attract my attention, and I don't know how to fit them together to make an overall picture, but I hope some of you will think about some of them. So some that I'm going to go through, this is this list of odd pieces of gravity. Work-out radiation, I'll talk to you more about, the quiet dog effect. Here I have already mentioned this, that black holes aren't losing mass right now. And if we go instead of to horizons, as I mentioned, because you have to know the whole future of the universe to know exactly where the horizon is to great precision. You want to depend on apparent horizons, but these have the strange property of being correlations between data at space-like related points. You have to look at a sphere, or a topological sphere, and find out that the light rays, all the light rays are going in at all points of that sphere. And that's at some fixed time, and therefore these different points are not talking to each other. And so it's hard to see how they're going to reliably talk about producing some effect. Other things I'll mention here, the chemist's thermodynamics. That is, the thermodynamics you can do without talking about the constituents of matter, but just talking about its behavior, as chemists did in the 19th century, some of whom didn't believe in atoms, but nevertheless they believed in Carnot cycle and things like that. So the chemist's thermodynamics doesn't really work for gravity. I think I'm going to say that more length a little bit later. But we do, of course, if you accept that the chemist's idea of entropy is inapplicable, we still have to see whether that means that some of its difficulties will be reflected in the various statistical or information-related concepts of gravity. So now I'll start on the first of those odd topics, what I call workout radiation. The thought occurred to me that I could become slightly immortal by sending out a signal that would go through the universe and witness my existence. And the simplest signal I could think of gravitationally, because gravitational waves don't get absorbed very rapidly, is just take a couple kilogram weights and do a changing quadrupole moment, okay? Now I'm generating gravitational waves according to classical gravity, and I wanted to ask myself, what hope do we have that those waves will ever be visible? And so I went to this and raised the question of, in view of semi-classical quantum mechanics, does it really look like a wave? What I've just done. Is the gravitational effects of that really look like a wave? Of course, it would be a long wavelength, one light second in length, which is several times the distance from here to the moon, so they're big, long wavelength things. But anyway, how well does it work? So I asked how many gravitons were in that wave. In one cycle of radiation, how many gravitons were involved? And you could figure that out because you know the intensity of the radiation from the quadrupole formula. And you know h bar omega gives you the energy of one graviton. So you just do that calculation, try to get the numbers straight, which I don't guarantee, but I think they're not too bad. And I came out with this result, that the number of gravitons per cycle of radiation, per wavelength, in this purported wave had a bunch of numbers that depended on my actually writing down a quadrupole moment for this motion. The mass, my kilogram in units of Planck masses, and the size of the quadrupole that I'm changing in terms of the wavelength of the gravitational wave, which, as I say, is this 1 light second. So we could put all those numbers in and see how much of a classical wave I'm generating. And the result is, well, first check that what we think is really classical works. The Hulse-Taylor pulsar, turns out that formula gives you about 10 to the 65 gravitons per cycle, so it's a good classical wave. We don't have to worry about it. But for this stuff that I was just generating, the formula gives 10 to the minus 14th. That means 1 graviton for each year, no, each 10 to the 7th years, 10 to the 7th seconds per year, and another 10 to the 7th before you get a graviton. So I would have to keep doing my morning exercises for 10 million years to get even 1 graviton out into the universe. So it's not a very efficient way to immortalize yourself, especially since you had to live forever to get it started. Right. Okay. So that's that one. So, but now we're going to work towards to see whether there's any hope on the intermediaries between the 10 to the 65 and the 10 to the minus 14 classicality measure. Is there something, if you could ever find a system produced fortunately for us by the universe, and this has been pretty good at delivering all kinds of interesting things on all kinds of scales, but if you could find a system that's had about 1,000 gravitons per period, why then in the waves that were coming out would show shot noise, because some of them would have 980 and some would have 1,020 gravitons, and there would be this variety, and it would be like Brownian motion, showing your atoms from the statistics of motion. You would show that there were gravitons if you could get. So that's the challenge for all the astrophysics-oriented people who know what crazy things can be found in the universe, to find something where the missing radiation would, being controlled by the quantum principles, would indicate that quantum principles were playing a name. So the fact that we're looking for something where quantum mechanics prevented things from happening, like it didn't let me radiate gravitational waves, I call these quiet dog facts. And by going to Google and putting in the dog that didn't bark, I came out with somebody who found this Sherlock Holmes story I remembered, and it even excerpted exactly what I wanted. And so this is a story where Sherlock is investigating a crime where a racehorse was either stolen or killed, I forget which, but certainly the trainer was killed. And so Sherlock is getting informed by the sheriff who'd looked into this crime, and the sheriff says, to Holmes, is there any other point to which you would wish to draw my attention? Sherlock Holmes says, to the curious incident of the dog in the nighttime. Well, the sheriff said, the dog did nothing in the nighttime. Holmes says, that was the curious incident. Why did the dog do nothing? And draws to the conclusion that whoever was involved in this was well known to the dog, and therefore that cut the list of suspects down immensely. So we're looking for cases where we would have liked things to happen and they didn't for some important reason. Okay, so there's been a lot of physics done with these quiet dog arguments. One of the earliest ones was Einstein in 1907. That's after special relativity, but 5 years before the Bohr atom. And quantum mechanics was barely begun with Einstein's contributions in 1905. But here he comes up with another one. He said that, well, if you have a solid, like a piece of a little bit over copper or whatnot, the chemists knew and worried about the specific heats. Instead of they thought it was made out of atoms, which would oscillate and be able to absorb energy. And if you want a half kT per degree of freedom, you get a specific heat of, I think it's 6 calories per mole or something. I forget the number. But anyway, there's a specific heat which at moderate temperatures the various metals that have been checked agreed, but at low temperatures it wasn't working. So somehow at low temperatures, a lot of these oscillations weren't occurring. And Einstein came up with the idea here, well, that's because the temperatures are so low that the one quantum that we have available exceeds what's available at that temperature. You can't get a whole quantum's worth of energy. That is a quantum in one of these oscillators. And so some of those oscillations just are unable to participate. So that's one of the early things where the absence of oscillation led to a conclusion supporting quantum mechanics to a significant degree, convinced some physical chemists to take it seriously, whatnot, very early in the game. And there are, of course, lots of other examples where we get somewhere by things that didn't happen. Neutrinos from the middle 1930s until 1955 or so, the only way we knew anything about neutrinos is that they weren't there. No one had seen a neutrino. You saw beta decay taking place. There were electrons coming out, but some energy was unseen. It had disappeared. And either you gave up energy conservation or you said, there's something we're not seeing that took it away. And so neutrinos developed for 2 decades without anyone ever having caught a neutrino. And then finally that was done. Likewise, our present stage with gravitational waves is the same situation. The Hulse-Taylor pulsar is losing energy. We can see that. No one's seen the energy yet. Where is it going? Well, no one had a good excuse where it could go in conventional, earlier days conventions of what could it be absorbing or hiding that energy. And it fit perfectly with the idea that it was gravitational waves. So the fact that there is energy losses that are unseen, that is the resulting emitted energy nobody has seen yet. We're still hoping to see it in the next few years from similar things. But anyway, that's again one. And the whole solar neutrino problem. Solar neutrinos were not reaching the Earth in the numbers that seemed to be necessary to account for the energy generation in the sun. And that was a mystery for a couple of decades, I believe, until finally people figured out that there was these neutrino oscillations, and the sun was emitting plenty of neutrinos, but they changed into mu neutrinos, which couldn't be detected by the detectors. So there are all these situations, and so the thing is that we were looking for more places in the universe where some of these things might let us draw conclusions. The most interesting would be, of course, if you could find something about the quantum that way. I don't think you could see energies; they would be too small. But if there are EPH, Einstein-Podolsky-Rosen type quantum entanglements, it could be that the phase of one piece of that entangled pair of degrees of freedom might never be seen, but if it could be shown not to be there, maybe we could conclude that there had to be some.
Why do you say quantum limits are inhibiting the radiation?
Well, for my example of this radiation, I can't get a wave out there because I can't generate a whole quantum's worth. I can't generate a quantum's I can't generate one graviton by the work I do in a half an hour,
well,
or even.
You're just creating a weak gravitational wave. That's okay.
Well, it's a weak gravitational wave, but one that can only be seen after millions of years. So the first many cycles of that wave aren't there. Before the first quantum comes, you haven't seen the wave. And if it typically takes 10 million years to get the first graviton out, why, it's going to be hard to see.
Maybe
I think
some detector of waves could see it anyway.
Yeah, well, I think it's like the specific heats. It's not that, what? Yeah, the photoelectric effect. That's right.
Well, but it depends on the detector.
Right. So anyway, anyway, if you can get around this, go to it. That's the whole point. So we would like to see some of these effects possible. Now, another whole set of questions that I referred to in connection with the definition of a apparent horizon. If you want to define, well, so this paradox is what Einstein called the spooky accident at distance, when there are actual correlations established at space-like separated points that you're unable to use that correlation to convey information from one of those points to the other, but nevertheless you can audit the effect after the fact and see that the correlations had existed when some measurements were made in the past. So EPR is sort of as I say, a three-stage process. You produce an entangled pair of something or other. Those things, when space-like separated from each other, get measured. You can't tell anything peculiar about that. Either of those measurements didn't look funny, but an audit sometime later, when that information was able to be collected and compared, you will discover, yes, you never get a violation of whatever spin conservation or whatever was they were controlling. So you can, if you, so there's this correlation between things that are not talking to each other. And we may need that if nature is to base anything like a firewall on an apparent horizon. Because an apparent horizon is something that you can verify, and presumably to get out the guns and shoot energy at you, nature would have to know that that apparent horizon was there, and that means it had to know information correlating space-like related points on the sphere that defines the trapped surface that guarantees that there will be a horizon someplace outside of it. So that whole thing might be needed, the very quantum mechanical things to get an effect. My own inclination would be to guess that nature is not that clever and is not going to produce any such effects on macro-sized black holes. But anyway, you need it. So, here's just a little more information, most of which I've said, about the EPR relationships. But the thing that's not so often emphasized is the fact that after the experiment is half done, and two things, whatever they were, a spin zero particle decaying into two spin a half particles, and then there's, if you measure one of those spins one place, the other has to agree to add up to zero. If the original, say, a pi zero meson started it with zero spin, the total spin of the decay products has to be zero, but they can't talk to each other. Since they're space-like related, depending on how you slice space-time, you don't even know which one came first. You could have a slicing this way or a slicing that way in your space-time diagram, and changes which one of those is assigned a time earlier than the other. But you can collect the lab books from these measurements, bring them together at some later stage and see, did it ever happen that the spins didn't agree as they were supposed to? Of course, if one of them is measured on the z-axis and another on the x-axis, there is nothing from knowing the first bit that tells you anything about the second one. So in those cases, but you can design experiments so you know in advance you're going to keep doing this with spins measured in the direction where they do influence, where they have to add up properly. And I would think that on an optical table these days, using photons instead of spinning particles or whatnot, people are clever. They could do Einstein, Podolsky, Rosen on an optical table, because after all, the distance on a table is just a few nanoseconds. It's the speed of light is 1 nanosecond per foot. The only useful bit of English measurement I know. So if you can generate a tangled pair of something, get it out on your table a couple meters apart, quickly measure. That's the important thing. Now you've got to be able to do the measurement of polarization or whatever it is within a picosecond or something so you've got time to record it in a semi-macroscopic piece of apparatus, then sends the information on later to get checked by the auditor to see whether it's consistent with the predicted correlations. So those kind of things can be done. But I don't think you're going to need it. However, this whole APR get business, as other people have mentioned, gets troublesome here. That's why we worry about it. Because if one of these two particles, instead of just going to the other side of your optical bench, was sent off into the universe and gobbled up by a black hole, why, the auditor does not have a chance to check it. Does that make a difference? If you can't check that this correlation had existed, maybe it didn't. But so anyway, the whole idea that some of these are in principle uncheckable because of experiments that fell into a black hole or whatever. Of course, there are lots of other ways to not be able to check it. Most things get sent out into the universe, don't get seen by anybody. That's the famous Olber's paradox. You look into the night sky and it's dark, which indicates that most of the photons being sent out by matter in the early universe don't survive to be absorbed. And we don't know, if we calculate what's going to happen to the light from the sun, most of it doesn't get absorbed in the solar system or in surrounding plasmas, but we'll end up, you may as well model it with a de Sitter horizon in the future to say it's lost, but it's effectively lost in most cases anyway. So there are all these things that we have to worry about in a curved space-time that are different. If you do EPR in Minkowski space-time, it's always in principle possible for the results of two experiments to somehow get compared in the future. But in curved space-time, either due to the black hole horizons or due to the Minkowski horizon or due to just the emptiness of space and things unable to be caught up with, there get to be things that you, in principle, cannot compare about that. So,
excuse me, Charlie. So,
yes.
So on that point, if the auditor were to fall inside the black hole also, he could do the auditing.
Well, if he got there soon enough, because
if the information got to him soon enough.
When you fall into a black hole, all the material that goes in gets crushed into a singularity pretty quickly, and if you're a little late getting started trying to chase it, you can never catch it.
That's true. Yeah. So
yeah.
He has to get there quick enough.
Yes.
I also take up this point because I mentioned it briefly the other day.
Microphone.
Do we have a microphone? Yeah, so I'd just like to also take up this point because I mentioned briefly a calculation by Gerard Milburn at the University of Queensland. And what you can do is, in de Sitter space, you can solve exactly for the propagation of electrons. So you can take an electron, a pair of entangled electrons, and actually then figure out what happens to that entanglement in de Sitter space. And also, I think he did it for the case of accelerating electrons. And the upshot is that the radiation associated with the horizons destroys the entanglement. It decoheres the entanglement. And that had better be the case, because we could make a black hole from a ball of n particles entangled with n exterior particles, and we would then have exponentially more hair in the black hole than you would predict classically. We would have n parameters that we would know internal to the black hole from keeping that information. And so it seems that it's an inevitable part of the properties of black holes that the entanglement has to be destroyed, in the case of the black hole, by the Hawking radiation. So I'm pretty sure that's the resolution of this. And so we don't need to worry about the audit.
Okay, thank you. Well, now I go on to my next topic, which is gravitational entropy. Again, as another puzzle piece, peculiarity of gravity, is this whole idea that if you try to use strictly thermodynamics to worry about gravitational entropy, you don't feel comfortable about the results. Of course, when entropy was first all the rage in the late 19th century, why people were talking about the heat death of the universe, how eventually everything would come to the same temperature and there would be no evolution, nothing exciting would happen.
Well, actually, if there's a cosmological constant, then we suffer a different kind of heat death after all in the long run.
That's right. Yeah, we have to look at a lot different. But anyway, the point is that nowadays the talk is not about the heat death of the universe. As you say, with the cosmological constant, it looks like it's going to just empty itself around most remaining pieces. But what we do is look back in the early universe and we see the heat birth of the universe. Nothing looks more like a high entropy equilibrium state than the various stages of the hot Big Bang, where, except for fluctuations that fortunately get amplified eventually, the content of the universe is essentially a hot uniform plasma. And what really happens, of course, is that gravity doesn't treat entropy in a way that that chemistry does, and that's because self-gravitating systems have negative specific heat. That's been pointed out several times. I have a few references that'll probably show up in the next slide or so. But anyway, the Virial Theorem tells you that for Newtonian interactions, I'm thinking of a globular cluster or something like that, if it should boil off a few stars, it would lose energy and collapse a little bit, and everything would move faster. Yes?
That's, of course, not an equilibrium system, so
That's
a crucial point.
That's right. But of course, the crucial thing about negative specific heats is they tell you that systems are not stable and you can't expect equilibrium. And that's what makes our universe so interesting, is that it looked uniform at the beginning, and that wasn't stable, and it began all this structure formation, which is related to the idea that you can export energy and get hotter.
But you have to think very carefully about applying equilibrium concepts to non-equilibrium systems.
That's right. That's right. And therefore, my conclusion from this, and also as mentioned by Lyndon Bell, of course, talked strongly about the negative specific heats, but it was Fang Liji, I think, who first, to my knowledge, made it a central point of the development of the universe, development of structure in the universe, to think about that. He has this nice little book written for students in China, which got translated eventually into English, and it's not very mathematical, but he goes through very simple physics and explains that there are these consequences of negative specific heats of gravitating systems. And
it's in one of the old editions of Landau-Lifshitz,
aha,
when they proved that specific heat must be positive. They have a little footnote and says, perhaps the student is wondering how stars can radiate energy and get hotter. Which, of course, the student is not wondering. And they say, oh, that's because our proof doesn't work with long-range forces.
oh, Well, it doesn't,
It's in
does,
some old edition of Land O'Licious.
it doesn't work with attractive forces, I think was the critical
But actually, I
problem.
don't think they gave the right answer.
Uh-huh,
I think
Yeah.
it's because the system is metastable.
right, yeah,
Which is more what Emil was saying.
yeah. Anyway,
It,
Fong made a big point of this and made a nice, clear case for the idea that this is one of the, Fong,
found.
yeah, that this is one of the most critical features for understanding the universe, and the fact that interesting structures have developed. And Freeman Dyson came up with that same idea quite independently and has published it a different place, but Fong had several years head start on that. So there are these references that take that viewpoint, and I think it's a very important viewpoint to realize that, that self-gravitating systems are only quasi-stable, but to the extent you want to treat that as near stability, they have negative specific heats. And secondly, the other thing to do is that the chemist's thermodynamics says you compute everything by having essentially reversible traps, paths from one place to another in your space of descriptors of the system. And unfortunately, as Oppenheimer and Schneider announced in the title of their paper on continuing gravitational collapse, that sufficiently large self-gravitating systems simply do not have a equilibrium from the point of view that they were taking, which is what you can see of the system. It's always changing. Well, it changes exponentially, so these days we tend not to think it's done, and that a black hole is a fixed object, at least the visible parts of it, and, in my opinion, much of the lost parts of it inside the horizon, which stay at curvatures less than what we're experiencing in this room now in some big billion solar mass black holes. There's a lot of regions inside where I can't imagine the physics would be changed from the standard results of classical physics. And so we think there is a lot of physics going on there. But anyway, the conclusion is that I take is that you can't trust the 19th century concepts of entropy, which are independent of the construction at the reductionist level of what it is you're talking about, whether there are atoms or not, etc. Didn't matter to calculate the efficiency of steam engines. But I think that because this is true, we must say that the thermodynamic entropy ceases to be defined, and we have to worry about whether or not, when you introduce the more information-related ideas of entropy, how are they threatened by this fact that the effective field theory that looks at these things without the microscopic picture to back it up, whether that fails so badly that the microscopic picture has to be perhaps changed in some way. So that's a threat that I think we have to worry about, and which I don't propose to give any answers to. So that's my collection of odd things about gravity that I wanted to tell you about.
If I have a box of gravity,
A box
Microphone.
microphone. Oh,
if I have a box of gravitons, which is not too heavy, I'm allowed to think of it as a usual Planck gas, no?
well, a box of gravitons is hard to arrange. You have to have a special universe to make the mean free path of a typical graviton shorter than the size of the universe. They're so hard to catch. So boxing.
You're worried that there's no walls.
Yeah, right. Yeah, so I mean, it's great to have. Well, this gets us to a whole other thing that I haven't, I think, included in my list of slides today. Right, but there's a class of objects, well, maybe I don't have that much more time either, class of laws of physics that I call evanescent laws, laws that work for a while and then get outwitted by nature. For instance, the Coulomb law loses its relevance once you're at JPL doing the ephemeris of the solar system. They don't include the charge of the planets in that, or the Coulomb forces between the planets and so forth. Why not? Because electromagnetism is too strong. It grabs everything and makes it pretty much neutral, and gravity is the only relevant force. So Coulomb's law is thrown in the wastebasket once you're doing the motion of planets in the solar system. Likewise, here we saw entropy is in danger. The chemist's entropy just doesn't apply once you get large gravitating systems. And energy, so I call that an evanescent law. It worked fine over huge domains, but then it reached its limits. It either was undefined or wasn't behaving right, or it didn't give you any insight of the system, or something was going wrong with it. Energy has the same problem, that once you've got what's now called dark energy, the idea of conservation of energy isn't getting anywhere. It doesn't help you side any problems, because the universe just has to expand a little bit. However much it wants to expand, all the necessary energy is there. You don't have any limitations on the expansion from the conservation of energy. You take a sample of the universe, you pull on it on all sides, expand it. And the work you've done pulling on it leaves the density inside the same, even though you've got much bigger volume. And so the conservation of energy is somehow being cheated out of relevance by nature's ability to figure out this scheme of exponential expansion and essentially cosmological constant type stuff. So we'd have to expect that every once in a while laws that we've lived with for years and loved are either going to be irrelevant or occasionally don't really fit, and often don't provide any insight, so you can ignore them while working with in some other method. But anyway, that's just a few extra added remarks. Thank you.